Thank you so much for the introduction, Olaf. My name is Nick Casetti, and I'm a fourth-year PhD student in the Coley group at MIT. And today I'll be telling you a little bit about my work in probing reactivity with neural network potentials. To contextualize my work in the center, I work on developing algorithms, specifically uh, specifically explore mechanisms for reaction prediction. So to motivate this a little bit, in data-driven reaction prediction, reactions like the one shown here are difficult to predict due to their sparsity in a lot of databases, as well as their complex bond formation patterns. However, being able to predict reactions like these is very important since these reactions are often key in natural product syntheses. So instead of thinking about predicting this in one shot from the reactant, we could imagine instead computing the reaction mechanism. To do this, we need some potential energy surface, and we need to be able to explore this potential energy surface. So by exploring this potential energy surface, what we can find is a reaction pathway connecting the reactant to the intermediates, and finally to our product of interest. And then along these pathways, we'll find these stars or transition states. The energetics of these transition states will help dictate the kinetics of the reaction, help tell us which are the more feasible or more likely reactions. In the prevailing method, prevailing potential energy circuit that's used for predictions like these currently are DFT potential energy surfaces. However, DFT for explorations like this can get prohibitively expensive. So in this work, as opposed to using DFT, we look to use neural network potentials. The reason we want to use neural network potentials is they are able to provide us DFT quality energies at a much lower cost because they learn from reference quantum chemical calculations. However, the rub here is, of course, that neural network potentials are only able to be accurate in and around the chemistry that they're trained on. Fortunately, for the chemistries that we're interested in here, we can use AIMnet2 reaction, which is a model from the IZIEV group that's able to accurately model neutral closed shell reactions with carbon, hydrogen, oxygen, nitrogen, which will allow us to model some of the reactions key in natural product syntheses. So now that we have our potential energy surface, introduce the method for exploring the potential energy surface, which is reaction mechanism exploration via automated machine learning potential calculations, or revamp. So the first step of this method is we have to determine which intermediates we actually want to go about exploring. And so the way we'll go about this is a well-known method called graph-based enumeration. And graph-based enumeration basically is a strategy for enumerating our intermediates to get our elementary steps. And the way we go about this is we combinatorially pick bonds to break and form. And we do this until we have our pool of intermediates. This results in a combinatorial explosion of the pool. And so methods will often limit this to 2 bonds broken and 2 bonds formed. The issue with this is some of the reactions that we're interested in may break or form more bonds. And so in revamp, we choose to break and form up to 4 bonds in order to capture these more complex elementary steps. Another issue with graph-based enumeration is that it doesn't see stereoisomerism. And so you don't effectively probe stereoselectivity. To overcome this, we enumerate the possible stereoisomers, which allows us then to appropriately look into what the potential stereoselectivity of reactions, the potential stereoselectivity of reactions are. And so now that we have this large pool of intermediates, how do we go about actually screening them? And so what we want to do here is thermodynamic and kinetic feasibility assessment. So we go back to our toy potential energy surface with our reactant as this orange dot. We find our intermediates, which we've enumerated on the potential energy surface. And the first thing we can do is thermodynamic feasibility assessment, which basically just means to eliminate steps that are going to be highly endothermic, as these are unlikely to be relevant kinetically relevant reactions. With our remaining elementary steps, we can evaluate their reaction paths with neutral elastic band and transition state optimization. And this then allows us to eliminate any reactions with kinetic barriers we believe to be unfeasible. The remaining transition state geometries are then passed to a final DFT refinement. And post this DFT refinement, we are left with a single step of a chemical reaction network with relative barriers. We can then recursively perform this entire workflow to build out our chemical reaction network until we have thoroughly and fully explored it to the extent that we are interested in. Now that we have how this workflow works, we can move a little bit into some results, some examples. And so, for example, this tetraene example, one step of this workflow reveals this 8-pi electrocyclization, and a second step reveals this 6-pi electrocyclization. What's great about this reaction path is that despite not encoding any of these rules, we are able to achieve correct stereospecificity according to Woodward-Hoffman rules. Another example is looking into some stereoselectivity of Diels-Alder reactions. So for this specific reactant, we're able to achieve both the cis and trans as kinetically relevant reactions. And this is something that is seen experimentally. Whereas in this case, where the only difference is that we've tethered this ring, the cis isomer goes away entirely, which is once again consistent with experiment. And to finally bring it full circle back to the original example, we are able to actually find the reaction path of the classic Nicolau synthesis of N-nitric acid C from this reactant here. And so, as we can see, Revamp is capable of, exploring some of these more complex reactions and providing experimentally known reaction paths. Looking into a little bit of the future of this work, one future direction for us is looking at how we want to apply this in more experimental workflows. And so we've looked at sigmatropic rearrangements and looking how we can use these barrier calculations as a computational feasibility assessment, and then using these feasibility assessments to screen for interesting reactivity in Coconut, which is a natural product database. And we've actually found a very interesting Claisen rearrangement to a natural product, and found that our pathway there is a relatively general strategy for synthesizing beta quaternary ketones. A separate direction, which is expanding Revamp to larger types of reactivity, specifically catalysis, looking at the Buchwald heterogemination and identifying and debugging failure modes. This is a much more challenging space since the bulky palladium ligands have resulted in some interesting potential energy surface shapes that result in multiple transition states. That means we have to effectively globally minimize these transition states to find the optimal route to most accurately reflect the kinetics. Thank you so much for listening. I'd like to thank the Coley group and all my CCAS collaborators, of course, as well as the NSF. And I'd be happy to take any questions.
All right. Thanks, Nick. And also, of course, thank you for staying on time. We're going to have always time to have one question. And for everything else, we will have to refer people directly to the speaker. Any questions? Going.
I had a quick question. This was really cool. I imagine if you're looking at like a multi-step process where you're looking at reactions where 1 to 2 or even to 4 bonds break, I could see the number of different options being enormous, especially for a complex system. Is there any sorting that you do, or like kind of determining which would be unreasonable?
Yeah, so in the enumeration process itself, we do a thing called constrained graph-based enumeration. So for more than 3 and more than 4 bonds breaking at once, we require there to be a double bond involved. And so this is a strategy that limits it to more reasonable selections. But another thing that we do, so I didn't have time to go over, but in the thermodynamic feasibility assessment, we actually have a 2D graph neural network trained to basically eliminate particularly unreasonable intermediates. And this evaluation is very rapid. So it's for AMET2, you are on the order of CPU seconds. For GNN, it's on the order of CPU milliseconds or GPU milliseconds. And so you can then evaluate a significantly larger pool and help kind of cut down before you start generating conifers.
That makes sense. Thanks.
All right.